Computation Framework demonstration. DynPaC is a Geant open code project led by the University of the Basque Country. One of the main features of the DynPaC framework is that it provides resiliency. In DynPaC, gold services are guaranteed with a backup path. In case of link failure, this backup path is automatically installed on the network. Here you can see the topology that we are going to use to demonstrate how the resiliency works in the DynPaC framework. First of all, we are going to check that there are no flows installed in the devices. This way, when we request a DynPaC service, we are going to see how it automatically programs the devices on the network. In order to request a DynPaC service, we need to specify a name, and we also need to select the source and destination nodes and the ingress and egress port. We also need to specify the duration of the service. DynPaC is going to check if there are resources available for the requested service in the entire period of time that we specify. We also need to select the bandwidth that we want for our service and specify the source and destination MAC addresses that they are going to use to characterize our service in the network. In addition, we can also select if we want this service to be a gold or regular service. As you can see, the service has been requested, and if we go to the DynPaC terminal, we are going to see how this request has resulted in the generation of a new snapshot for this specific service, called Service Backup. Now we can check how the service has been properly installed in all the devices of the network. DynPaC selects the shortest path for the services, so in this case the service has been installed in the switches 1, 6 and 4. If the link between switch 1 and switch 6 goes down, the DynPaC automatically reacts and installs the new service in the network. Now, if we check, we can see that there are no flows installed in switch 6, and instead, flows have been installed in switch 2 and 3. The DynPaC framework supports service scheduling, thanks to its time-dependent resource consumption awareness. In this second demonstration, we are going to show how the different snapshots are generated in the DynPaC framework. We are going to use Postman for quick service request. First, we are going to reserve service A. If we go to the DynPaC terminal, we can see how the snapshot has been generated. Here we can see that only service A exists in the snapshot. Then, if we request service B1, we are going to see how a different snapshot has been generated, which includes service A and B1, maintaining the previous snapshot, now divided in two, where only service A exists. If we do the same with services B2 and B3, we are going to see how the three services are requested. These services are using the same resources, but they are doing it in different time slots. DynPaC is clever enough to figure this out and creates different snapshots. We can see how in these new snapshots, service A and B2 exist, and service A and B3 exist, but B2 and B3 never exist together. Finally, if we request a service C of the same duration of service A, we are going to see how all the affected snapshots are updated. In order to optimize network resource utilization, the DynPaC framework implements a flow disaggregation algorithm. For this demonstration, three services have already been requested to the DynPaC framework: service A of 8 gigabits, service B of 5 gigabits, and service C of 7 gigabits. DynPaC assigns the shortest path to the services taking into consideration the resources available in the network. Service A goes from switch 1 to switch 4 through its shortest path. Service B goes also from switch 1 to switch 4 but for an alternative path, and service C goes from switch 2 to switch 4. We can check how the flows have been programmed in the network devices. In switch 1, we can see how the flows of service 1 and service 2 are installed. We can also check how in switch 2 the flow entries of services B and C exist. With this situation, if we request a service D from switches 2 to switch 4 with 9 gigabits per second, we don't have enough resources in the network to allocate it, unless we disaggregate. In these cases, the DynPaC framework calls the path computation element and studies how the services installed in the network can be disaggregated by using the information available through the traffic pattern analyzer interface. In this situation, the path computation element is telling us that by disaggregating service B, we can make room in the network to allocate this new service. Now, if we check how the devices are programmed, we can see in switch 1 that service B has been disaggregated into 3 different sub-services, thanks to the OpenFlow granularity, and now we are able to allocate service D.